Thanks. It's a pleasure to be here. Today I'm going to talk about some statistical methods, which is kind of different from the theme of this week, which is design. So I apologize if some of you are expecting to see more design aspect. This talk is going to be more about how to define the quantity of interest and how to do the estimation of that. So this project actually is motivated by multiple micro-randomized trials that we've been involved in that have binary outcome. So one example is the BariFit micro-randomized trial, which is briefly mentioned by Susan. So bariatric surgery is a treatment for those people who are severely overweight. So we're talking about people with BMI over 40 or over 50. And after they gone through the surgery, it's very important for them to keep doing exercises and to control their food intake. Otherwise, their weight rebounds very quickly within a few months or within a year or so. So in the traditional setting, these weight maintenance are supported by these in-person sessions. So, for example, the patient would meet with some healthcare provider once a week, something like that, to report his exercise and to help monitor his status. But these in-person sessions, they have a problem because it's very burdensome, and the participation rate is not very high. So, and therefore, maybe mobile health intervention is a potential alternative to these in-person sessions. So here we're looking at a micro-randomized trials that are looking at developing mobile health interventions to help maintain weight for these people who've been through bariatric surgery. So I'll talk about briefly what's the data and what are the intervention components. So the data are collected from Fitbit trackers, which records the patient's step counts, and also the patients are asked to report their weight once a week, report into an app. So they're asked to measure their weight once a week, and they're suggested to record how much they eat every day. And to keep them from by doing physical exercises and to help them log their food intake, the micro-randomized trial has multiple intervention components. And today we're going to focus on the last one, reminders to track their food intake. So this is a reminder that can be sent every morning to each individual via text message, reminding them to make sure you put into the Fitbit app how much you eat every day. And we're going to assess the effect of that. Okay, so this is the data that we see for each individual. So we have observation, and then a treatment as an indicator, whether the message is sent or not for every day, and then we measure an outcome. So in this particular case, the outcome would be whether the person actually completed his food log on that day. And we're going to use HT to denote the history information accrued up to decision point T. So all the information known before deciding on whether to send a message or not at the time T. Okay, so I'm going to talk a little bit more about each of these notations. And so decision points, these are the time points that are decided by the researchers. That usually they're the time points that the treatment might be most beneficial. So for example, in the BariFit example, the food track reminders are sent every morning because the patients are supposed to start logging their food intake starting from the breakfast. So And in this study, the patients are in the study for 112 days, so approximately 4 months. Okay, so treatment indicator, this could denote whether a treatment is provided at a decision point. And also for some cases, the treatment indicator the treatment can have multiple levels. So the treatment indicator can take values more than 0 and 1. But in this talk, for simplicity, we're going to assume that the treatment indicator takes 0 and 1 values, is binary. And we're going to denote by PT the randomization probability. So the randomization probability in general could depend on the information accrued up to that time. And it's important that the randomization probability is known to us, to the investigators. And that's the key to these randomized studies. And in the benefit, the text message of food track reminder is sent every morning with a probability of 0.5. So here, in this special case, we have a constant randomization probability. But in general, it could vary based on the information you observe. Okay, so here we use the term proximal outcome. This is something that's measured after each decision point. And usually this is a quantity that represents what the treatment is directly targeting. So here, the treatment is a text message reminding the user to track his food intake. So here, the outcome, the corresponding proximal outcome would be whether the user actually logged his food on that day. And here, the outcome is binary because we define the outcome to be 1 if the recorded calorie is greater than 0. So if he recorded anything at all, then it will be yes. Otherwise, it's no. And at the end of this talk, if we have time, I'll give an extension where the proximal outcome can be defined over a duration where other treatments could be provided. So this actually corresponds to what Susan has described in her talk, though. The fraction of time of being stressed over the next hour where other treatments could be provided. But here we start from the simpler case. And note that I'm using t+1 as the subscript of the proximal outcome. This is just to remind me that the proximal outcome is measured after AT. So that's why I increment the subscript by 1. Just note that. Okay, in observations, okay, so OT is observation that is accrued between 2 decision points. So notationally, it can also include the outcome, or you can think of the proximal outcome as a function of an observation during that time period. So O1 includes baseline variables, and in benefit, in this example, the observations that we have include how many steps you took during that day, and user self-report, including their weight, weekly weight measure, and also we have baseline variables like age, gender, and their baseline BMI. And another variable that's included in observation is the availability indicator. So Susan has already touched on this. I think this is a very special thing in micro-randomized trials. Sometimes the researchers might deem it inappropriate to provide an intervention based on safety or ethical considerations. So for example, if the treatment is a message that interrupts the individual, then it might not be ethical to send the message if the individual is detected to be, for example, is driving. So, and we will see that the treatment effect will be conditional on availability, because we are only interested in the treatment effect when the individual is available for treatment. we'll see more of that later on. And in this particular example, for the food track reminder, because it's sent first thing in the morning, there was no availability issue. Every individual is available every day. Yes, please.
Are we in a situation where randomization even makes sense? Like, for example, if someone's kind of busy, they might seek treatment, but without really doing too much. I'm just curious about it, of course, because the idea is that we have a little more specific randomization. It's not like, hey, message for 10 p.m. It's something more like, if you send messages, we can purpose such that then this message will go to 10 p.m. But our idea is not because of who's done, biggest idea is actually going like it at the right times, but let's try to look at what's working well, what time from when should we actually set this stuff, and when should we investigate on interventions.
I see. That's a good question. So you're essentially, if I understand it correctly, you're saying how do we model or how do we assess the responsiveness of an individual that could vary over time, right? So you will see that I think this talk might partly answer the question because we will be looking at treatment effect moderations by observed covariates. So in that sense, these covariates might provide guidance regarding what is a better time, better opportunity to send a treatment. Okay, yeah.
So if you follow up on that question, I think what are the possible external responses could be wavering overcome by I might be able to tell you, yeah, I'll send you a message every time it's happening, but not so
Yeah, I think that's a yeah, that's a good point. So in one of our other studies, Heart Steps, which sends messages to the individuals to increase their physical activity, increase their step counts, we actually allow the individuals, to specify what are the time frames that you prefer us to, so that we might send you a message during these time frames. Yes.
Scrum design is about how design doing ranking. A lot of other analysis is like doing it and doing that, but then you really should use it to do like your analysis design is not just the proxy method on it. Analysis design is definitely.
Sorry, I don't quite get the question.
I guess maybe something clarified it helps, but I guess what I like about the suggestion asked about this one from analysis design is that it's getting solved this problem of how to do interventions. Not by that down like you just sort of be like. It's doing it by actually changing what you're doing like. This session is not like it's actually changing the actual observation you have. And I think this is a pretty common theme in insurance study was when you come up with a better technique on that you have. This is when you be collecting some extra variables. So I'm just curious if there's some equal observed like in these discussions with the next deep question. Before the start session,
Well, I'm not sure about the keywords or terms, but my understanding is the following. So these micro-randomized trials, they're aiming to develop or to optimize these interventions. So to collect data maybe in a better way by asking these questions, or to analyzing the data in a more if you use statistical jargon in a more efficient way, you increase the signal to noise ratio. I think both of these approaches are for the same end goal, is to optimize or develop a better mHealth intervention. That's my understanding. If you want to add to it. Thanks. Okay. So, okay, let's move on. I borrowed this idea of conceptual models from one of Susan's other talks. So, I think it helps us to put our act together. So, this is the data we have, and we know there's a randomized study, although this is not a classical randomized trial. It's quite different from the standard randomized trials. But usually, how would one approach to analyze these data? I think usually a data analyst would fit a series of models with a series more and more complex models. For example, a first model one would fit would be something like this, where we have an intercept term for the treatment indicator. And a second model one might fit would be something like this, an intercept term with a treatment indicator and an interaction term. So here ST would be some kind of interesting moderator variables that we want to look at. So, and the meaning in here I'm using the squiggle very loosely, so don't put any real math onto that yet. But the meaning of these coefficients in the think about as a classical randomized trials. The meaning of, for example, beta 0 would be the effect of the treatment that's averaged across time, averaged across people, averaged across all the other variables that's observed up to the treatment time. And similar here, for example, beta 1 is the differential effect of your treatment with a 1 unit increase of your moderator that's averaged over all other variables. So, so I think one of the goals of this project is that we want to develop statistical methods to model and estimate the treatment effect while be consistent with the scientific meaning that people usually have with these beta coefficients. And also, another, I forgot to mention, so this part that only involves pre-treatment variables, these are usually thought of as control variables that are used to reduce noise in, for example, analyzing randomized trials. And it's known, Susan also mentioned that in her talk, that it's known that adjusting for these variables is a robust way to estimate the treatment effect. So you don't need the control variables to be a correct model for anything. So in our method, we also want to have a robust way to utilize these control variables. Okay. So to mathematize the problem, we're going to use the potential outcomes framework, and you've seen these from Susan's talk. So I'll just iterate very briefly. The over bar denotes a sequence of variables up to time t. And this would be the potential outcome of the observation had the individual been through the treatment trajectory of that. And similarly, we can define the potential outcomes for the proximal outcome and for the history. Okay, so now we're going to use the potential outcomes to define the treatment effect that we care about. So suppose now I'm in the study, I'm at time t, I've been through the treatment as it's been assigned to me. Now I'm looking at what my outcome would be. Would I complete the food log today if I was sent a message this morning versus if I was not sent a message this morning? Because this binary outcome, we're taking an expectation of each. So we're making a contrast between two excursions. Again, the word excursion came up. So the two excursions would be following the treatment up to time t-1, then receive treatment, versus following treatment up to t-1, then receive no treatment. We're making a contrast of these two potential outcomes. And we might be interested in seeing how the treatment depends on some interesting moderators or treatment effect modifiers. So let ST be some subset of the history information observed up to that point. So ST could be some time-varying covariates. It could be some baseline variables. And we do the conditional expectation given ST, meaning that we are averaging over all other variables in the history that are not included in ST. And we're going to see some examples of different choices of STs on the next slide. And finally, the treatment effect is also defined on conditional on the individual being available. Because if the individual is not available, then we don't care what's the treatment effect at these time points. And we take a log because I think this looks familiar to those who have worked on the binary outcomes. This is a log relative risk. Alternatively, one could work with logistic regression, in which case one may look at log-odds ratios, and there are a lot of debate regarding which one is preferable over the other. We choose to use this for various reasons. If I have time, I'm going to talk about that at the end. But for now, let's say this is the estimate, the treatment effect that I care about. Okay, so some examples of the treatment effect. If we, here I set ST equal to 1, meaning that I actually don't include any moderator in the variable, don't include any moderator in ST. So this would be a average treatment effect that's averaged over all the variables in the history in H of t. And here, suppose I include day in the study in the moderators, then this would be the treatment effect of interest. And of course, people could put models, parametric models on these treatment effects, and that's what we're going to do. Okay, so before we move to the estimation, this is a standard causal inference stuff. So we want to connect the estimate that's defined using potential outcomes to something that's defined on the observed variables. So we're assuming consistency, we're assuming positivity, and we're assuming sequential ignorability. So consistency means that, essentially it means that the message I received does not affect the outcome of some other people. So in this situation, it's quite plausible, but in certain cases, for example, if the users are divided into teams and the intervention are targeting each of the teams, for example, if there's a leaderboard or something like that, then one might need to generalize this notion so that to allow one person's treatment assignment to affect another person's outcome. But in this particular example, this assumption holds pretty good. And positivity assumption says that at each time point, we're always exploring. So the probability of assigning each of the treatment options is always positive. This allows us to actually, at the end of the day, make the contrast and see what is the treatment effect. And sequential ignorability, this also holds by design of the micro-randomized trial because we decide the randomization probability. Okay, so now this is also a very standard causal inference that the potential outcome, that the estimate defined using potential outcomes can usually be written into two ways. One is iterated expectation, and the other one is using inverse probability weighting. Okay, so first we are going to consider a special case. We're going to consider the special case where the treatment effect is conditional on the entire history information observed up to that point. This is not the scientific goal we're actually going after. We're going after a scientific goal where we want to average over some of the variables. But considering this special case actually helps us to motivate our estimator for the marginal effect. So we're going to first look at this. But for here, let's suppose that the oracle comes down and tells me that, if you select this particular ST variable, then this relationship holds. Let's just suppose that. Here ST could be a rather complicated function, right? Because theoretically, the left-hand side is a function of h of t. But let's assume that for now. Now, what one would usually go about estimating beta here, the parameter of interest, is that one would impose a working model on the denominator. So this would be something like a expected outcome on the node treatment. Then, if the working model is correct, this means that we have the mean model of the, sorry, I missed the AT over here. It should be in the conditional expectation. This means that we have a mean model of the outcome given history and given the treatment. Right. So if we have a mean model, then I would say, we can use GEE to estimate the alpha and the beta. But the issue with that is that we need the working model to be correct in order to guarantee the consistency of the GEE estimators. So, in other words, to improve that, we want to only assume the top part of the model, and we don't want to assume the working model for the treatment on the, the working model of the outcome on the node treatment to be correct. When we assume something, now here I'm going to talk very loosely about semi-parametric models, so if there's some expert in the room, please forgive me. When we assume something that's parametric, part of the model is parametric, and part of the model, we don't put assumptions, meaning that it's non-parametric. This is usually called semi-parametric models, and there has been a vast amount of literature on semi-parametric models, and one of the goals of this literature is to find consistent estimators and hopefully more efficient estimators under these less restrictive assumptions. And actually, it turns out that for this particular model, Robin's work, his work on structural nested mean models has very close relation to this type of models. So on the next slide, I will show you what's his estimator for beta, and we're going to develop our estimator based on that. Okay, so there's a lot of stuff on this slide, and don't worry, we're going to take a closer look to this estimating equation. So here's the estimator. The estimator, alpha hat and beta hat, solves this estimating equation, means that the alpha hat, beta hat makes this equation 0. And the Pn here is just the notation for 1 over n summation I from 1 to n. Okay, so this estimator that's derived based on Robin's work, it's semi-parametric locally efficient. What that means is, one, it's robust, meaning that the estimator beta hat is consistent for the treatment effect we care about with any choice of the control variables. So we don't require the control variables to be a correct model. And another good thing about it is that it's locally efficient, meaning that the estimator beta hat for the treatment effect has the smallest asymptotic variance if we actually get a correct working model for that. So to summarize briefly, it's robust, it's almost always consistent under certain conditions, and if you actually get the working model correct, then it's the most efficient, or it has the smallest asymptotic variance. And the V, though you can think of this as some kind of weight here. It has a rather complex form, and I think the message here is that Vt is a function of H. Okay, so here I want to delve a little bit more into this estimating equation, because understanding why it's robust helps us to motivate our estimator for the marginal effect. Let's look at the blue term and the red term. So the blue term can be decomposed into two terms. One is this term. This is the outcome times a negative treatment effect multiplied by AT. So if you're familiar with Robin's work, this is called blipped down outcome. And it has this nice property that its conditional expectation equals the outcome under no the conditional expectation of outcome under no treatment. And the other term in the blue term, the other part in the blue term is a function of H. And here, the red term, AT minus its randomization probability, is a centered treatment assignment. Now, these observations makes it so that the blue term and the red term are orthogonal to each other with any choice of G. And this is the key aspect that makes this estimating equation robust to different choices of the control variables. Okay, so so far we have considered, and we're gonna see something very similar to this when we talk about how to estimate the marginal treatment effect. Okay, so far we have considered when the treatment effect is defined fully conditional on H of t. But of course, what makes more scientific sense is when we marginalize over variables that are not in the moderators of interest. So scientifically, this is of more interest because it aligns with people's usual understanding of treatment effect. And another argument in favor of this definition is statistical. So for here, H of t, information observed up to time point t, it could be very high dimensional because we have many, many time points in the micro-randomized trial. So t could be very large and ht could be very complex. So it's hard to say, oh, if you're able to impose some sensible model or a correct model over here. But for this, the left-hand side is a function of s of t. And s of t is of our choice. We can choose s to be only an intercept, or it could be an intercept plus some interesting moderators. So we have a better chance of having a correct or a sensible model for this estimate. Okay, so now I'm going to talk about the estimator. This is just rewriting the semi-parametric efficient estimator. And previously, I talked about that these two terms are orthogonal to each other, but now, when we change the modeling assumption to only on the marginal effect, these two terms are no longer orthogonal. So, and the following is a way to make them orthogonal. So here's the estimator. We first choose some probability p tilde that's within 0 and 1, and the p tilde only depends on the moderators of our choice. Then we form weights, and we center the treatment by the p tilde probability, and then we plug those in. The use of the weights and the centering of the probability makes the blue term and the red term orthogonal to each other again. And this weighting and centering technique has been also used in another paper of our lab, which deals with the continuous outcome situation. Okay, so here I'm just rewriting the estimating equation for our method. This is classical asymptotic statistics that we can show that the beta hat from this estimating equation is consistent for the beta, and it's asymptotically normal if we have this model correct. And it's robust, and yes? Yeah. That's a good point. Thanks. So I will. So the choice of the p tilde, it affect. I have a separate slide to talk about the choice of p tilde, but here the asymptotic results. If we have this model correct, then the asymptotic results doesn't depend on the p tilde. So it's always consistent. But p tilde, of course, you need to choose it between 0 and 1, and it needs to depend at most on S. Okay, so right to your question, choice of p tilde. So if the treatment effect model is wrong, then p tilde plays a role. So p tilde determines what's the limit of the estimator from your estimating equation if your treatment model is wrong. And one can derive a general formulation, and here I'm giving a simple example that's more interpretable. So for example, if we only include intercept in the moderators, then the p tilde needs to be a constant. So suppose it's a constant within 0 and 1, then the estimator beta hat would converge to this quantity. So in a sense, this is an averaged relative risk over time. And not strictly, but intuitively, that's the interpretation of this term. Now, if the treatment effect model is correct, then this would reduce to the beta over here. Okay, so to sum up, the choice of the p tilde helps to determine the limit of the estimator when you don't have a correct model for the treatment effect. Okay, so now I'm going to talk about one simulation study where we try to make the distinguishment between the two estimators that we have seen. Okay, so here's the generative model. This is the treatment effect part, and this is the outcome under no treatment part. And we choose the covariate ZT to take values from 0, 1, and 2. I started from trying to set up the most simple generative model by choosing ZT to be binary, but in binary situation, we don't see a difference between, in binary ZT, we don't see a difference between the two estimators. So here we're, the next simplest situation is ZT taking 3 values. And here is how we set up the control part. It's nonlinear in ZT. So this would be the true treatment effect under this generative model. If we conditional on the entire HT, then this is the true treatment effect, which depends on ZT as we set it up. And here, this is the treatment effect when we average over HT. So this would be a single number. So in the in the semi-parametric locally efficient estimator, the estimator that we've seen first, that's derived based on Robin's work, we would need this model to be correctly specified. Now, suppose in the analysis model, we're setting the moderators to be only an intercept, then this model would not be correct. A working model for this would not be correct. So one would expect the locally efficient estimator to be biased. Whereas for this model, it will be correct. So the method that the second estimator that we've seen for the marginal effect will be consistent. And this is what we see. We see the bias and standard deviation and the root mean squared error and coverage probability of 95% confidence interval. Here's the results for the robust estimator, the second estimator we've seen. Here's the estimator that we derived from Robin's work. And for comparison, we also included a GEE. And as I said on the previous slide, we see results as expected. So this is consistent, and these two are biased. Yes? This is the estimation for this quantity, actually. This is the estimation for this quantity. In other words, so here I'm writing out what's the true treatment effect under the generative model. But suppose I don't know the true generative model, and I'm given two estimators, right? Two estimators as I presented here. Then I want to use two estimators both to estimate the marginal treatment effect without including any moderators. Then one estimator would be biased because one estimator requires this model to be correctly specified. If you only include an intercept, this is not correctly specified. Does that answer the question? Okay, so how much time do I have? Okay, great. So we're going to talk about analyzing the data set that motivated this project. So as a reminder, the individuals are sent a food track reminder every morning with a probability 0.5. And there are 45 participants. Each of them are in the study for 112 days, so 112 decision points. And the proximal outcome is whether the individual completes his food log on that day. And we're going to use this conceptual model. So we're going to consider the marginal treatment effect. And the control variables that we put inside the G include day in the study, gender, and food log completion on previous day. The role of the G variables are to reduce noise, and one could expect that food log completion on previous day should be highly correlated with whether you complete a food log on the current day. So we include these variables in the control part. And here is the estimated result for the marginal treatment effect. Of course, we have seen in the simulation studies that when we're doing this estimation, we probably want to trust more the robust estimator. But in this particular case, the two estimators gave rather similar results. So, and to put in the context, if I average over all people, all decision points where no message was sent, the food log completion rate was about 50% across all time, across all people. So here the 0.014 means that the food log completion rate is improved by about 1%. By about 1% of these among these individuals. It's not a very, I don't think this is a very significant result. Of course, I'm not using the word significant as statistically significant. I don't think that's a big effect to me. And of course, the result says that no effect is detected from the data. So that's the conclusion of this data analysis, that the data indicates there's no detectable effect of the food track reminder text messages on the food log completion of that day. And here are some of my thoughts based on this data analysis. So, for example, there might be some ways to improve this food track reminder so that we might be able to see a larger effect. For example, right now the food track reminder is sent as a text message every morning, so it's ignorant of the individual's contextual information. It only knows what time is it and how many days the individual has been in the study. Now, if the reminder could be incorporated as part of a mobile phone app, then one might be able to utilize other contextual variables to better inform what is a better time what is a better occasion to send a message. And another situation, this is to improve the effectiveness, trying to improve the effectiveness of the treatment. And from another aspect, if we think that the treatment, the food track reminder, might not be that useful after all, then we might want to combine that with other messages that are sent in the morning. So actually in the study, there are other messages that are also being randomized in the morning. So for example, there's this so-called varying daily step goal. Every morning the individual receives a message telling them to, try to achieve 10,000 steps today. And sometimes the user receives a message trying to achieve 12,000 steps today. So receiving multiple messages in the morning might be burdensome and might irritate the individual. So if we're not going to consider looking at the effect of the food track reminder in the next iteration of the study, then we might want to combine the food track reminder with other messages. So get rid of the randomization part of that treatment component. Right? This is to reduce burden. And of course, I would welcome other comments if anyone has. Okay, so this is the extension I mentioned at the beginning of the talk. This extends the definition of the proximal outcome to be defined over a duration of time during which other treatments might be provided, as in the example in Susan's talk. So this is the definition of the, this is the observed data for each individual, and the proximal outcome could be defined as a function of the information observed after AT up to in a subsequent window of length delta. And in that case, actually, this would look very similar to the quantities presented in Susan's talk. So here, in this situation, we're contrasting for an individual, if he is following treatment up to time t-1, given treatment, then no treatment for the following window, versus no treatment and no treatment for the following window. And the estimating equation is also very similar. The only difference is that we have this inverse probability weighting, so that we upweight those individuals who experience the treatment trajectory as we would like to estimate. Okay, so to summarize, we talked about a definition of causal excursion effect for binary outcomes, and we looked at a semi-parametric locally efficient estimator for the effect that's conditional on the entire history observed up to that point. And this estimator motivates a simple and robust estimator for the treatment effect that's marginalized over all but a small subset of interesting moderators. And that's the estimator that we think makes more scientific sense. And we looked at an extension to settings where the proximal outcome is defined over a duration of time, where other treatments may occur. And we looked at an analysis of the marginal effect of food track reminders in the benefit study. So that's all of my talk, and I welcome any questions. Let me see. Here is that one. Yeah, I guess I could. Yeah. Yes. So for example, yes. So the choice of whether we want the excursion to include future treatments is a decision made by the investigators. So if in the smoking cessation study, because the treatments can potentially be provided every minute, whereas the outcome we're looking at is the fraction of stress time over the next hour. So because of that choice, we want to involve these treatment indicators in defining the excursion effect, because we want to look at if the person is treated now and not treated for the next hour versus the person not treated now and not treated over the next hour. Whereas in the example that I talked about, the food track messages, because the treatment is targeting the user's food log completion on that day, so it makes sense that the proximal outcome is defined immediately after the treatment. So it won't involve other future treatments. Does that answer the question? Yeah, this is more of a defining the research question, defining the estimate. That's a great question. I apologize that I should have read the literature more carefully so that I'm able to answer the question, but I'm not that familiar with the study right now, so I can't answer that. But if, yeah, we would need to change this part. That's right. That's right. Yes. So I think there are two answers to this. One is from a scientific point of view, and another is from a statistical point of view. So from scientific point of view, I think there are pros and cons of each, and there's a lot of debate in the literature. And what I see that convinces me the most is that one disadvantage of log odds ratio is that it's non-collapsible. So maybe you have heard of Simpson's paradox. So log odds ratio if the log odds ratio for each of the subgroup is, say, positive, then it could be that the log odds ratio when you combine the groups are negative. So this is one issue that people have raised about log odds ratio. And another thing I think is, at least in my understanding, log relative risk is easier to understand and easier for domain scientists to model, because we're only talking about probabilities or fractions, whereas odds ratio is another layer of complexity. But of course, this is just my personal opinion. And another answer from the statistical aspect is that if we want to model log odds ratio instead, then it's much harder to find a robust estimator like the one we have here. So that's another reason. Thank you very much.